So today, I'll wait. So today we are going to be adding, subtracting, multiplying, dividing functions, but you already know how to do that. So what we're going to do today is to focus on why it's important to identify the domain before you add, subtract, multiply, or divide functions, to take it to that next level of difficulty and deepen our understanding. So we're not just doing all of this algebra and creating these new functions without thinking about where am I restricted? Where are the only places that I'm allowed to create this function? Also, when you're adding functions, like say you add a parabola and a line, what do you get? What's the new function going to be? Is it a parabola? Is it a cubic function? If you're multiplying, dividing, what kind of output, what kind of new function are you creating? So that's something else to keep in mind. So big idea though today is, what is the purpose of finding the domain of the individual functions before I perform an operation, add, subtract, multiply, or divide? So let's start by unfreezing the screen right here at the top of the page. Okay, so what is important for us to remember? Okay, we can add, subtract, multiply, and divide functions to create new functions. Stuff we already know. Now I'm just going to ask you to think about what type of functions you can create and where can you create these functions? Where will they graph? So here's the conditional statement. So we have sums, difference, products, and quotients of functions. If f of, oh wait, I'm color coding here, possibly red. If f of x, and I'm just going to go to my black pen instead of purple. So that purple was supposed to be black all the time. And blue for g of x. If f of x and g of x, back to the pen, and then we'll just stay in the pen for a while, are functions. Okay, so first, that's the first condition. They must both pass the vertical line test. They must actually be functions where each x has only one y as an output. So that's one condition. And how did I write that a second ago? Hang on a second, I am so sorry. They share x's meaning that they have x's in the domain in common, then I can add them, subtract them, multiply, and divide them. But these are the conditions that must exist. They have to be functions, and they have to share the same domains in some places, have common x's. So let me get my pencil out here. We're going to be adding, subtracting, multiplying, and dividing. And I'm color coding here, so I'm going to grab my red pen up. So if we're doing the f plus g of x, really I'm doing the f of x plus the g of x. And hopefully what this will allow you to see is that I'm going to add their y's. If they have x's in common, then I can add their y's. So I'm just going to, so I don't have to switch back and forth between colors, put all my f of x's in these statements. So I'm going to take all of these y's for my function f, and I'm going to switch to my blue, and I'm going to add the y from the g function, g of x, g of x, g of x, and over g of x. However, when I put a function in the denominator, I have to mention, as long as g of x does not equal 0. So when we're doing a rational function where we create, excuse me, excuse me, when we create a rational function, we divide two functions. We always create an additional restriction, or often create an additional restriction, because we'll put an x in the denominator. Okay, so this is just another form of the f plus g of x, the f minus g of x. But what I think this helps you to see is that you're adding y's or subtracting y's, right? Because f of x means y, right? Multiplying y's or dividing y's. That's what you're doing when they have common x's. So to sum it up, we can, not in blue, pencil, we can add, subtract, multiply, and divide y's wherever the x's are common. Or in other words, where the domains of f of x and g of x intersect. I can add their y's if they overlap in their x's. And I'm going to demonstrate this right now in Desmos using these two equations right here. Given f of x is equal to the square root of x plus 5 and g of x is equal to the square root of 3 minus x, find the domains of f plus g, f minus g, f times g, and then the different domain of f over g. So let me see where I put Desmos here. I thought I had it opened up. Okay, so let me just take a look at this real quick. And this was x plus 5, right? Is your f of x, and I have that in red. And then my g of x was in blue, so I'll change that. Okay, and then, so here we have the picture of the two functions. Okay, so you can see with our f of x, our red function, that our domain is from -5 to infinity. Because if I put anything less than -5 in my square root, I'll end up with an imaginary number. With my g of x, the largest number I can put in for x is 3. If I put in 4, I have 3 minus 4, that's a -1, that's imaginary. So listen, if I want to add them, I can only add the two functions where the two functions overlap in their domains. Like for example, right here. What's my y right here? 0. And then my y for my blue function, or my g of x, is up here at 2.9 or 2.8 something, right? If I add those, 0 plus whatever that is, I'm going to get whatever that is, right? So watch. Look at my new graph. This is the graph, my new graph, of the f of x plus the g of x. Notice where the new graph lives. It only exists in the domain that the two individual functions share or intersect. Do you see that? What if I subtract them? Might want to scoot it up so we can see it a little better. Again, do you see that the graph only exists where their domains overlap? Or what if I switch and I do g of x minus f of x, because that's different, right? Right? G minus f is different than f minus g. But still, the graph only exists where their domains overlap. How about f times g? Look at that. Hey, Sarah. Okay, and so now what happens if I divide the f of x by the g of x. Now I put the g of x in the denominator, and the g of x is my blue function. So what's my 0 of my blue function? 3. Can I put 3 in my denominator? No. So watch what happens to my graph when I divide and put g in the denominator. Look at the graph. It approaches, it's got an asymptote. It just goes forever and ever and ever, up, 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 approaching 3, but it'll never reach 3. It's an interesting looking graph. Now, what if I switch it, and instead I put the f of x in the denominator? So my f of x, if you recall, is this red one. What's its 0? -5. I can't put a -5 in the denominator here because that would create a 0 in my denominator. Look what happens. I'm just going to I'll approach -5, but I'll still never reach it. So when you put a function in the denominator, you have to remember there's an additional restriction. You can't put a 0 in the denominator. So it's always a little bit different to find the domain of a quotient versus the domain of a sum, a difference, or a product. Okay, so back to what we were working on. All right. So let's take a look at algebraically doing this instead of looking at it at a graph. So I'm going to pick up my red pen, and the instructions say, find the domain of f plus g, f minus g, and f times g. So let's find their domains individually. So we have f of x is equal to the square root of x plus 5. And what we know about square roots is that the radicand has to be non-negative. So x plus 5 must be greater than or equal to 0 in order for us to graph a valid square root function. So x must be greater than or equal to -5. We know this. Okay, now let's find the domain of our g of x. So that would be 3 minus x under our radical. And we know 3 minus x must be greater than or equal to 0. So let's see, that's -x is greater than or equal to -3 because we'll subtract 3 to both sides. Then we'll divide by -1. And we get x is less than or equal to 3 because when we divide by a negative, we have to reverse our inequality. So let's talk about our domain. So I'm going to get a domain number line here, our x-axis. I missed my iPad because I can make straight lines. All right, so I'm going to grab my red pen, and I know that my domain for my f of x is from -5 to infinity. And the domain of my g of x is from -infinity to 3. And so if I want to add, I'm going back to my pencil now. The question says, what is the domain of f plus g, the f minus g, and the f times g? The domain of all of them will be the same domain. The outputs will be different. The functions you will create will be different, but their domains will all consist of the points from x equals -5 to x equals 3. And that's critical. If I want you to graph this new function, it's important to know, well, what x's can I pick? Versus just randomly picking a bunch of x's and not being able to graph many of the points. So it's kind of a work smarter instead of harder idea. Identify the domain first. All right, so that answers all of those questions. Do you have any questions? Okay, then let's move on to part B. Remember what we saw when we did the division of these two functions. We saw an asymptote. So, all right, I'm going to create a fraction here where I'm going to put my f of x, which is the square root of x plus 5. And here's what we know. Its domain is from -5 to infinity. We already found that. And then our denominator we get the square root of 3 minus x with the added restriction that it cannot equal 0, right? So its domain would be from negative infinity to 3, but open on the 3, not closed. Because I can't put a 3 right here, can I? I can't, because that'll create a 0 in the denominator. But everything less than 3 would be okay. So again, if I were to graph that on a number line, just to look at it graphically here, I know that from negative 5 to infinity, it'll work for my numerator. And in my denominator, from negative infinity to 3, but open at 3, because I cannot put a 0 in the denominator, and a 3 would create that. And so, let's answer the question, what's the domain of f over g? What is it? Where does the overlap begin? Negative 5 to 3, open, right? Not closed. And so, asymptote. Because you've created a rational function, you have to consider those vertical asymptotes. All right, so now that we've identified the domains, we should be able to very quickly add and subtract and multiply and divide these functions. So if you're okay, I'm not going to color code anymore. Are we good? So f plus g of x in alternate terms means the f of x plus the g of x. And we're just adding their y's for the domain negative 5 to 3 closed. So those are the only x's we're allowed. We're going to add the y's that belong to those x's. So that would be the square root of x plus 5 plus the square root of 3 minus x. And then, of course, you must simplify your answer if you can. And I'm wondering, can I add those? Is it possible for me to add those two things? Like, for example, if I have the square root of x plus the square root of a, can I add those? It's not like the square root of x plus 2 square roots of x. I can actually add those because these are like radicals. That's 3 square roots of x. I can add that. These are not like radicals, and therefore I am done. The f plus g of x is equal to the square root of x plus 5 minus the square root of 3 minus x over our defined domain where the functions are defined. Okay, you guys go ahead and do f minus g of x and then come back to the press pause, finish it, check your answer, come back. Okay, so over the domain negative 5 to 3 closed, you should have gotten the answer square root of x plus 5 minus the square root of 3 minus x. Now let's multiply. So multiplying f of x times g of x over the same domain, negative 5 to 3, that's where we've defined our domain, we would get the square root of x plus 5 times the square root of 3 minus x. Now these I can multiply. I can. Just like if I were over here and I did the square root of 2 times the square root of 8. That's the same as saying the square root of 16, which is 4. I can multiply radicands underneath square roots. So this could look more like this. And I would require this. And not only that, I would ask you to simplify what's underneath your radical. So we get the square root of 3x minus x squared plus 15 minus 5x, and then continue it out. So we'll finalize this. The f of g of x, the f times g of x is equal to the square root of negative x squared. That's going to give me a semicircle minus 2x plus 15. So here's what I know. The f times g is going to give me a semicircle. Okay, over our defined domain. Last one. Here we have the f of x over the g of x. We're creating a rational function here. This would look like this, the square root of x minus 5 over the square root of 3 minus x. And just like the idea, did I do that right? It's a plus 5, right? Thank you. All right. Just like the idea is I can multiply them under the square root. I can also divide them under the same square root. So this could also look like this. X plus 5 over 3 minus x underneath the radical. And then just remember that your domain still has to be defined, but I bet you can really see what x is not allowed to be here in your denominator, right? From negative 5 to 3, but open at 3. We've already defined it. We had defined it up there. But now you can see it down here. And you can't simplify that anymore. There's no common factors, so that's done. Questions about that? Okay. So we had a couple more to practice. Now what we're doing is we're adding, subtracting, multiplying, and dividing a parabola and a line. So it's not two radicals. It's two different types of functions. So what are we going to get if we add a parabola plus a line, or a parabola minus a line, or a parabola times a line, or a parabola divided by a line? Be thinking about what is my final function going to look like? What is it going to be? So first let's find our domains, and I'm not color coding anymore if you're okay with this. The f of x is equal to x squared minus 1. This is a parabola. Quadratic, right? Domain, unrestricted. Anything I want. There's nothing that I'm not allowed to use. For my g of x, x minus 1. This is linear. Lines also do not have restrictions. If they're functions, they don't have restrictions. Okay, so therefore, there's our little symbol for therefore if you haven't seen it before. We're going to draw a conclusion. If I'm going to add them, subtract them, or multiply them, the f plus g, the f minus g, and the f times g have domain of negative infinity to infinity because that's where they overlap, everywhere. Okay? I don't think that's a stretch to understand that. Let's take a look at this one though. The domain of f of x over g of x. So that would be x squared minus 1 over x minus 1. Now I've introduced a restriction. There is a restriction in your denominator. X cannot equal 1. In my numerator, my domain is everything. In my denominator, x cannot equal 1. So where do they overlap? So the domain of f over g is from negative infinity to 1. Punch a hole in the number line right there at 1, because you have what we call a vertical asymptote, union 1 to infinity, right? Because they share everything else, but there's going to be a hole in the graph. Maybe it's going to be a hole. It depends on what kind of graph it is, or it's going to be a vertical asymptote. Okay? All right. So now let's add, subtract, multiply, and divide them. So if I take a parabola, sorry, this is supposed to say, I'm just going to rewrite it, f of x plus g of x. And I take a parabola, this is something you should know, x squared minus 1, and I add a line, x minus 1. What do you think I'm going to get as an output? What's my new function going to be? What do you think? Well, let's look at it. So that's x squared minus 1 plus x minus 1. Let's combine like terms. So the f plus g of x is equal to x squared plus x minus 2. What's that? That's parabola. So when I add a parabola plus a line, I get a new parabola over the domain everywhere, all the x's. So when I add a parabola, so basically this was a parabola plus a line equals a parabola. Just a new parabola, a different parabola. Let's subtract. Let's do a parabola minus a line. See what we get. So f of x minus g of x. So that would be x squared minus 1. Remember to use parentheses here, minus x minus 1. Critical to use parentheses on this minus g of x because it is a binomial, because you have to distribute. So x squared minus 1 minus x plus 1. And then we combine like terms. So the f minus g of x equals x squared minus x. So what did we get? A new parabola. So a parabola minus a line is also a parabola over the domain that is totally unrestricted. So adding parabolas and lines gives you parabolas. Subtracting parabolas and lines gives you parabolas. Now what if we multiply a parabola times a line? What do you think?
New parabola.
New parabola? I heard somebody else say a cubic. Well, let's see. So this is the f of x. This is a times sign, a really big, ugly one, times the g of x. Okay, so we're going to do x squared minus 1 times x minus 1. And we multiply that all together. That's x cubed minus x squared minus x plus 1. Can't combine like terms. So the f times g of x is a cubic function. Right, because an x squared times an x is an x cubed. So it'll create a cubic function. So basically, when you take a parabola times a line, you get a cubic function. Interesting. That should happen. Over the domain, unrestricted. Now, if when you multiply a parabola times a line, you get a cubic, what do you think is going to happen if you divide a parabola by a line? Parabola over a line. Oh, let's see if you're right. You guys are pretty smart. F of x over g of x equals x squared minus 1 over x minus 1 with the added restriction that x cannot equal what? 1. Because that would make a 0 in our denominator. So there's an asymptote or there's a whole. Now we have to simplify this fraction right here because you must always simplify fractions. So what I see in my numerator is the difference of squares. So I could factor that out to x minus 1 times x plus 1 all over x minus 1. And when you're working fractions, you must always simplify their common factors. In this case, their factors are just binomial factors. So that cancels that, leaving you with the final answer, and you must do it. F of x equals x plus 1 as long as x does not equal 1. So that's linear, yes?
Yes.
So in this case, we got a line with a hole in it somewhere. Actually, at the hole at x equals 1. That's where we got a line. I mean a hole. That's what we got. Okay? And then, of course, our domain, we could say, in other words, all reals as long as x does not equal 1. If we don't want to write it in interval notation, we don't have to. Okay, so that could be our domain there. So there you go. Things that I'd like you to think about when you're doing these problems. What kind of function am I creating? Okay, lastly, we are almost done. I don't think you need me for this. The f plus g of 2. That's the f of 2 plus the g of 2. So basically, what does that mean? You're plugging in a 2, right? So that'd be 2 squared minus 1 plus 2 minus 1, or 3 plus 1, right? 4 minus 1, it's 4. 3 plus 1, did I say minus? So here's what I know. the f of 2 is 3. Right here, we figured that out. Right here. And the g of 2 is 1. We figured that out right here. And we just have to do that over and over again. But this time, we're doing the f of 2 minus the g of 2. So 3 minus 1, which is 2. This is so hard. And the f of 2 times the g of 2, which is 3 times 1. Oh my gosh, it's horrible. Or the f of 2 over the g of 2, which is 3 over 1. Oh my gosh. I better not give you any homework. That's horrible. Okay, you get it. You didn't need me to refresh that. Okay, so homework's on not on Canvas yet, but it will be 1 through 9 odd. A lot like these problems here. And then 17 through 23 odd. Listen, you have to do 80 million things for, I'm exaggerating, but like 14 things for each problem, 17, 19, 21, and 23. Basically, all of the things that I just did right here for 2 problems. You have to do for 4 more. Okay. Yes, and you better do it because you got to know how to find a mate for tomorrow's graphing. Algebra is not as bad as graphing. Okay.